In this lecture, we're going to talk about the semi-inverse method. Now, we've seen that we can come up with a set of combined compatibility and equilibrium equations for isotropic stress-strain materials, and that we get the Beltrami-Mitchell equations. And we've kind of talked about already how that it can be difficult to solve that set of simultaneous equations, even subjected to some fairly simple boundary conditions. And so there are all kinds of different ways to come up with simpler ways of solving those equations. And one approach is called the semi-inverse method. So this alternative approach is to assume a certain functional form of stress or strain or displacement fields, and then we can see if the other equations are satisfied, such as compatibility and equilibrium. Now, I've written all of these equations out in terms of index notation. Equilibrium sigma ij comma j, that's a first derivative of stress components with respect to spatial position, plus the body force. We do have an implied summation over the j term. We have compatibility, epsilon mn comma ij plus epsilon ij comma mn is equal to epsilon im comma jn plus epsilon jn comma im. Those involve second derivatives of the strains with respect to spatial position. That would mean third order components in terms of displacement. So anything that satisfies strains being first order, we don't even have to worry about what we get. Those will automatically solve compatibility equations. So any first order strain field, that means something times x, something times y, something times z, will automatically satisfy our compatibility equations. And we are going to restrict ourselves to looking at isotropic stress-strain relations. So with the Lemay coefficients, we're using sigma ij is equal to lambda epsilon kk Kronecker delta ij plus 2g epsilon ij, or, and we showed how we derived this previously, strains in terms of stresses, epsilon ij is equal to sigma ij over 2g minus lambda over 2g 1 plus 3 lambda plus 2g sigma kk Kronecker delta ij. So in this lecture, we'll start off with a simple hydrostatic state of stress. We're going to go through and convert from that assumed stress state to the strain state, to the displacement equations that will integrate from the strains based on small displacement, small strain theory, and see what we get. And we'll go through that process. There will be a lot of examples of dealing with partial differential equations and systems of partial differential equations. They're not in such a format that we need to take a matrix approach to solving these equations, but we're going to go through and we're going to kind of solve this puzzle and see how we can get various displacement fields and so forth that do satisfy equilibrium compatibility for our isotropic stress-strain relations. I'm going to break this lecture up into several parts. We're going to take a look at least at a few different examples. I have 3 in mind, and I'll make a different lecture for each of these 3 that I have in mind right now, and if I get time, I will go back and I will add some additional examples at a later time. So our first example is going to be looking at a hydrostatic stress state. We've talked about hydrostatic stress states previously, but just to kind of illustrate it on a stress element or stress cube, we can imagine there being a pressure acting in all 3 perpendicular directions simultaneously. This would be normal stresses. That would be all the pressure P. So in this case, sigma x and sigma y and sigma z, sigma 1, 1, 2, 2, and 3, 3, are all equal to whatever that value of pressure is, and if the pressure is acting inward, that would be equal to minus P. Now our shearing stresses tau xy, tau xz, and tau yz would all be equal to 0. Alright, well, let's take a look at what our strains would be in this case. And I had written this down on the previous page, but let's go ahead and write it down again. There are different forms that we can write our constitutive equation for isotropic materials. I'm using this one in terms of Lemay coefficient sigma ij over 2g minus lambda over 2g 1 over 3 lambda plus 2g sigma kk Kronecker delta ij. Well, let's take a look at one of our strains. We really only need to look at one. All three will be the same, since the stresses are the same in all three directions for an isotropic material. But for example, sigma x will be equal to, well, sigma 1, 1, or sigma x over 2g. So that's equal to minus p divided by 2g. Then we'll have minus lambda over 2g, 1 over 3 lambda plus 2g. And then we have sigma kk, which is the trace of the stress tensor, or the summation of the three normal stresses added together. And in this particular case, that is minus 3 times p. And we have Kronecker delta ij. And if we're looking at the 1, 1 1, 1 strain component, that's in the x direction, then Kronecker delta 1, 1 is equal to 1. And so this term turns on. We can do a little bit of manipulation with this. Let's find a common denominator. Like so. To simplify this out a little bit, let's go ahead and multiply the minus p through all of these terms. So we'll have minus 3 lambda p minus 2gp plus 3 lambda p divided by 2g times 3 lambda plus 2g. Now these terms with the lambda annihilate each other in this particular case, and the 2g also goes away, so we can simplify this down that the strain in the x direction is equal to minus p divided by 3 lambda plus 2g. And that will also be the same value that we would get if we went into the manipulations for epsilon x and epsilon z. If we wanted the trace of the strain tensor, which we'll call little e, or we can call epsilon kk, that would be epsilon x plus epsilon y plus epsilon z added together, that would be equal to minus 3p divided by 3 lambda plus 2g. Now we could have also expressed these in terms of our more familiar modulus of elasticity and Poisson's ratio. Now Hooke's law for that in the index form would look like this: minus nu over e sigma kk Kronecker delta ij plus 1 plus nu over e sigma ij. And so we can do the same sort of manipulations for our 1, 1 component or our x component. We have minus nu over e times minus 3p, Kronecker delta 1, 1, let's go ahead and write it down, which would be equal to 1, plus 1 plus nu over e times sigma 1, 1, which is equal to minus p. Well, let's do our manipulations on that. We already have a common denominator, so we're looking at plus 3p minus p nu over E. We're going to have a minus p that we can factor out. Oop, I forgot my nu term over here. We're going to have a minus p that we can factor out. And then if we do that, let's see what we've got. We're going to have a 1 minus a 2 nu divided by the modulus of elasticity. Right, so we'll keep those terms here for a moment. And previously we had written down the trace of the strain tensor as minus 3p over 3 lambda plus 2g. Well, there's a term called the bulk modulus that we can define. We can also write the trace in terms of the Poisson's ratio and modulus of elasticity. We can also write this as minus 3p times 1 minus 2 nu over E. Well, the bulk modulus is a term that we're going to define as k, and it's going to be equal to E divided by 3 times 1 minus 2 nu. So another way we can express the trace of the strain tensor is equal to minus p over k in this case. Now the bulk modulus is kind of related to this compressibility that we might have. Volume change under a hydrostatic stress state. We'll come back to the bulk modulus in just a little bit. But let's take a look now at our displacement fields that we can get from these strain fields. We're going to look at small strains such that the Almansi and the Green-Saint-Venant strain tensor are the same thing. We're going to have the form epsilon ij is equal to ui comma j plus uj comma I, where the comma denotes the partial derivative. We're going to use x, y, and z notation, and we're also going to use u, v, and w notation for displacement components u1, u2, and u3. I realize this may cause a little bit of confusion, but as I've mentioned before, these notational issues are a real thing when we start getting into a lot of these problems. Alright, well, let's first take a look at epsilon x. Oh, and I need a 1/2 in here. Epsilon x is equal to 1/2 partial of ui with respect to xj plus the partial of uj with respect to xi. If we add those two together for 1 and 1, epsilon x is equal to the partial of u with respect to x. Now we have an expression for epsilon x is equal to minus p times, well, let's see. Let's use the one with the Lemay coefficients in it. It's equal to minus p divided by 3 lambda plus 2g. So we can integrate a partial derivative with respect to x. When we integrate a partial derivative with respect to x, we're going to get a term that looks like minus p 3 lambda plus 2g times x and in addition to that integration with respect to x on that term, since we're integrating a partial differential equation, we could have some function of y and z that might be in u, such as when we took the partial derivative of this with respect to x, it didn't show up. So we do have to account for that. And we could have a constant of integration. Now that constant of integration is going to represent a rigid body displacement, as they usually do in these types of problems. And we'll talk about that in more detail as well. Now by the same reasoning, we can take a look at epsilon y. Epsilon y is the partial derivative of v with respect to y, and that's equal also to minus p over 3 lambda plus 2g. And so v, it's going to be a very similar form, but now we're integrating with respect to y. So we have minus p over 3 lambda plus 2g times y. And then we could have an arbitrary function, I'll call that f2, that could be of x and z, and another rigid body constant. Lastly, I'll write it over here, we could have epsilon z being equal to the partial derivative of w with respect to z. And when we integrate that, because that is also equal to minus p over 3 lambda plus 2g, we'd get w, the displacement component w, is equal to minus p over 3 lambda plus 2g times z, plus a third function that could be of x and y, plus c3. Now I'm assuming all these integrations make sense. If you have not had a class in partial differential equations or haven't had any experience with partial differential equations or partial derivatives even, it's probably a good time to go back and learn a little bit about that now at this point. Otherwise some of this may not make a lot of sense. But even if you haven't had that kind of class, I think you'll still be able to understand what we're doing here. We need to figure out what these functions and constants are and how they're related to one another. Now, one of the things that we mentioned at the beginning is that we didn't have any shearing stress. This is a purely hydrostatic stress state. There's no shear. So terms that look like the shearing strains, now epsilon 1, 2 would be equal to 1/2 partial of u1 with respect to x2 plus the partial of u2 with respect to x1. Well, the shearing strain gamma 1, 2, or we'll use gamma xy, would be twice as much as the tensor shearing strain quantity. So this would be something like the partial of u1 with respect to y, partial of u with respect to x, plus the partial of v, partial of v with respect to y plus partial of v with respect to x. Alright, so I'm going to label, let's do it in red, I'm going to label this as 1. I'm going to label this one as 2. So if we look at the shearing strain gamma xy, which is equal to 0, we can compute the partial derivative of u with respect to y and the partial derivative of v with respect to x. So let's do that. The partial derivative of u with respect to y. Well, we don't get any contribution from the first term since that's multiplied by x. And on the second term, we're going to have the partial derivative of f1 with respect to y. And then the constant, when we take the partial derivative, goes away. And then we're going to have plus partial of v with respect to x, and that's going to be equal to the partial derivative of f2 with respect to x. And since that's equal to 0, we can also say it's the partial derivative of f1 with respect to y is equal to minus partial derivative of f2 with respect to x. Now if we look at this carefully, and it's not really showing up until I write this more explicitly, so let's go ahead and do that. We have the partial derivative of f1, which is a function of y and z. Partial derivative of that with respect to y has to be equal to the minus partial derivative of f2, which is a function of x and z, with respect to x. Now, in order for that to work out, we're going to be kind of limited in what our functions f1 and f2 can look like. So let's see. If that is the case, they both could be functions of z, and they could be any order of z that there is right now. But since we have some function of y on the left-hand side and some function of x on the right-hand side, at most, f1 and f2 could be first order in x or first order in y. Alright, so let's keep that in mind. F1 and F2 could be at most first order in x and y, but z could be higher order. Alright, let's take a look at the next strain that we might have, maybe gamma xz. That would be the partial derivative of, let's go ahead and write it all the way out first. That would be the partial derivative of u with respect to z plus the partial derivative of w with respect to x. And that would also equal to 0. So the first one comes from equation 1, would be 0 contribution from the first term, and then we'll have the partial derivative of f1 with respect to z, and from the contribution on the the third equation, we'll go ahead and label that as 3. We have the partial derivative of this first term, which is 0, and then we have the partial derivative of f3 with respect to x, which leads to partial derivative of f1, which is a function of y and z with respect to z is equal to the negative partial derivative of f3, which is a function of x and y, and that's with respect to x. So by the same reasoning, let's see, y could be higher orders. If we just look at that equation I wrote down, y could be any order, but the functions f1 and f3 could be at most first order in x or z. Okay. Now you can do the same thing, and you can look at gamma yz is equal to 0, and you would find similar issues. You would have F2 and F3, and then F2 and F3 can be at most first order in, let's see, 2 and 3 would be at first order most in y and z. And just looking at that, then x could be higher order. But if we take all of these together, we can say some things about F1 and F2 and F3. And let's see, maybe I'll make a little bit of room on the next page so we can write that down. Alright, so let's take a look at that function F1. Now that function F1 was a function of y and z. Okay. Now F1, we said, could only be first order in y. And then on the next line we said F1 could only be first order in z. So these both would be first order in y and in z. Now if we look at F2, F2 is a function of x and z, and by the same thing, it could only be first order in x and z. And F3, which is a function of x and y, taking them all together again, at most could be a first order function in x and y. Alright, so let's say that F1 is equal to AY plus BZ. Okay, that's first order in y and it's first order in z. Now, on the previous page, we had a relationship that the partial derivative of F1 with respect to y is equal to minus partial derivative of F2 with respect to x. Alright, so let's say F2 is equal to some other coefficients. It's got to be first order in x and z. So maybe hang on here. Let's write this down first. So the partial derivative of F1 with respect to y would be equal to A and let's say we had F2 then, which is a function of x and z. I'm going to start to run out of constants here, so I'm going to put a little star by it. Let's say that this first order function for F2 was a star x plus b star z. Okay, so now the negative of the partial derivative of F2 with respect to x is going to be equal to minus a star. So another way that we can say this is that a star is equal to minus a. Okay, without dragging this out, we can go through and do a similar process to find all the other terms that we would have in these functions f1, f2, and f3. Let me write down what the result is. And so what we have here then is A, B, C, D, F, and G, which are our constants of integration. Now we do see that A pops up a couple times, B pops up a couple times, D pops up a couple times. It's kind of a nice symmetry to this. The coefficients C, F, and G. Now we didn't use little e because it's the trace of the strain tensor. But these coefficients represent a rigid body motion. And we can take those equal to 0 if we want. It doesn't affect the strain fields. It's just adding that offset to our displacements. We can also choose a coordinate system such that we can have, when x y and z are equal to 0, the origin of the coordinate system, we can place that at the same location so that the other coefficients are 0 as well. I should complete this and choose the system so that when x, y, and z is equal to 0, that u, v, and w are all equal to 0. And we can also choose it so that the rotations are equal to 0 as well. So omega x, omega y, and omega z. So we can get rid of any rigid body rotations as well. And then in that case, A, B, and D will also equal to 0. Now these stress fields satisfy equilibrium because it's a constant, and we're ignoring body forces. And then they will satisfy compatibility because these are only first order in the coordinates. For the displacement, in compatibility equation or displacement are third order equations. Strains are constant, and so when we take second derivatives of those strains, then those go away as well. Now the last thing that we can talk about to kind of complete this example, we did mention that the trace of the strain tensor is equal to minus 3p times 1 minus 2 nu over e. Now the trace of the strain tensor for small strains represents a volume change, the change in volume of a unit cube of this material. Now if we have a material who does not change volume, what that implies is that, well, we either got a rigid material whose modulus of elasticity is infinity. That's really not a real material. But for real materials, what that implies is that this relationship 0 is equal to 1 minus 2 nu. If we solve for nu, then that implies that nu is equal to 1/2. So materials that exhibit a Poisson's ratio, isotropic materials that exhibit a Poisson's ratio of 1/2 or approaching 1/2 are volume conserving materials. Now the most typical material that we would see that would approach this would be rubber. And it's kind of interesting when you pull on a piece of steel. The modulus, the Poisson's ratio for steel is about 0.3. You're actually changing the volume of that piece of steel. As it gets skinnier and longer, its volume changes, its density will change. When you take a piece of rubber and you pull on it, its volume stays about the same because its Poisson's ratio is about 1/2. So that's kind of an interesting result there. Alright, well, this will be part A, and then we'll continue on with some additional examples of solving these systems of partial differential equations. Now, one of the things that I want you to kind of notice as I work through these, it may not be something that you would be able to sit down and do completely on your own without some experience, but you kind of see the approach that I'm taking. Whittle away on it, work with your normal strains first, bring in your shearing strains, bring in your strain displacements, and just kind of start beating on these partial differential equations and arbitrary functions until we find out what we can get. In a lot of cases, we're only interested in the leading terms, on this page the x, y, and z terms. In some other cases, some of these other functions may have more interesting contributions to the stress, strain, and displacement fields.